while I'm doing that, I'll try to. Okay, today's agenda. First thing is like yesterday we went over uh, the basic graph traversals, and then we went over a couple of graph algorithms like PFS, TFS, and how will you manage the PFS traversal and DFS traversal, and also when the graph is disjoint and then you have to traverse using DFS and BFS. That was done. Um, and what else? And also we were able to manage yeah, and also we were able to manage uh, what BFS, TFS. What else we did? Yeah, we covered the directed and undirected graphs. So that was a couple of hours, I guess, that we spent. And then I had a lot of troubleshooting in my while I'm streaming. So today I think I hope I'll have less trouble troubleshooting the streaming tools and how to manage it. Uh, I hope the voice is clear. If someone's on the live stream and if you are not able to hear me clearly, just flag me immediately. I'll just post that comment as well. I hope that remains. If you have trouble hearing or viewing the stream, drop a comment. Okay. So now that's out of the way. So today I'll start with Dijkstra's algorithm, or I'll see whatever is there in one of the agenda or one of the materials and see if I can cover few problems related to that, problems related to DFS and BFS traversals only, and invite the participants. Okay. And in the meantime, if one of you have any questions, if any of you have any questions related to graph traversals, or sorry, graph representations, DFS, BFS, and disjoint graphs or disjoint sets, I think it's called. Feel free to post it here. We can go over those later. So that's that. So now that's out of the way. Let's dive in. Now I'll have a focus timer on, and then I think I'll try to take frequent breaks every 30 minutes or something. We'll limit the break time to 5 minutes or less. Let's dive in. Nothing else. Yeah, nothing else to be specified. This is my LeetCode. Thanks to LeetCode, they have made awesome content about interview preparation. Please do subscribe to LeetCode so that you can have access to this premium content as well. And I was going over Geeks4Geeks. That's a lot of extensive coverage. I feel that Geeks4Geeks is good, but it has pretty extensive coverage. Like to curate that itself is a big task. To curate the, I mean to curate whatever is there in Geeks4Geeks. And also I felt that when I have the Geeks4Geeks screen open, my streaming tends to get slower. It renders a lot of things, I guess, on the sides. So having a premium subscription, I'm not sure if I can have a premium subscription for Geeks4Geeks. That's the thing. I've always chosen it free. I think all the materials are available free. I think I hope it will be ad free as well somehow. So let me see. Let's go to graph algorithms and then let's navigate from there. Okay, yeah, I think this is trouble with opening GeeksforGeeks website alone. Other ones are working kind of fine for me while streaming. Okay, let me close this one as well. We are done with the BFS. Okay, so Dijkstra's tongue twister. Dijkstra's shortest path algorithm. Okay, let's go. Let me turn on the timer. Meantime. Okay, so I'll just check the task list. So this one is done. Okay, config. I'll just go to stay focused as 25 minutes and 5 minutes short break and 15 minutes long break. I might take a 15 minutes long break or 10 minutes long break when I go to have dinner now. So yeah, let's start our first focused time. So what do I want? I want the focus time, not the break. How do I select it? Delete this one. Okay, got it. Stay focused. Yeah, let's go. So how to find the shortest path from source to all vertices using Dijkstra's algorithm. You're gonna wait. Okay, and we kind of found the shortest path from source to destination using BFS as well. But what's the difference here? I'll just try to get that out of the way. So using Dijkstra's, we can find the shortest path for the weighted graph as well. In BFS, those were not weighted graphs. All the edges were considered as equal. Here, each edge has a specific weight. That's the difference. Given a weighted graph and a source vertex in the graph, find the shortest path from source to all other vertex in the given graph. The given graph does not contain any negative edges. Okay, if we have negative edges, there is a separate algorithm. So here, without negative edges, let's see. We have this graph. Let's go to this one. Dijkstra's algorithm using adjacency metrics. So the idea is to generate a SPT, shortest path tree, with a given source as a root, maintain an adjacency matrix with two sets. Okay. Generate a shortest path tree, the given source as root, maintain an adjacency matrix with two sets. One set contains vertices included in the shortest path tree. Other set includes vertices not yet included in the shortest path tree. At every step of the algorithm, find a vertex that is in other set and has a minimum distance from the source. Okay, I did not understand it. Focus. The idea is to generate a shortest path tree with the given source as a root. Got it. Maintain an adjacency matrix with two sets. One set contains vertices included in the shortest path tree. Okay. Other set includes vertices not yet included in the shortest path tree. Okay. Not yet included in the shortest path tree. At every step of the algorithm, I hope the audio is clear. Yeah. Yeah. At every step of the algorithm, find the vertex Okay. Okay. At every step of the algorithm, find a vertex that is in the other set not yet included, and has a minimum distance from the source. Okay. Create a set SPT, shortest path tree set, that keeps the track of the, okay. It is a bit confusing explanation here. Illustration. Let's see the illustration here. To understand Dijkstra's algorithm, let's take a graph and find the shortest path from source to all nodes. Consider the below graph. Source is 0. So source is 0. We need to find the shortest path to all the other nodes from 0. The set SPT set is initially empty. Okay. And distances assigned to vertices are from the same node to the other node, it's 0. And we have nodes 1, 2, 3, 4, 5, 6, 7, 8. All are in the serial same ordering. So we have this 8 nodes here. 4 plus 4, 8, yeah, where infinity indicates infinite. Okay. Now pick the vertex with the minimum distance value. The vertex 0 is picked, included it in SPT set. So SPT set becomes okay. So SPT set is another set which just have the um, which is initially empty, and we will be adding only the ones with the shortest path into that set. After including 0 to SPT set, update the distance value of its adjacent vertices. Adjacent vertices of 0 are 1 and 7. So 1 and 7 are the direct adjacent vertices from 0. So, and we know that all the path or the weights are positive numbers. So anything added to this one would be more than this. So the shortest path would be the direct connection here. Adjacent vertices are 0 of 0 is 1 and 7. The distance values of 1 and 7 are updated as 4 and 8. So for 1 it is 4, for 7 it is 8. Okay, the following subgraph shows vertices and their distance values. Only the vertices with finite distance values are shown. The vertices included in SPT are shown in green color. Okay, this one is included and this one's not. Pick the vertex with minimum distance value and not already included in SPT, not in SPT set. The vertex 1 picked and added to SPT set. So vertex 1 is picked and added. So SPT set now becomes SPT is shortest path tree basically. The shortest path tree set becomes 0 and 1. So we have added two of those this thing. Update the distance value of the adjacent vertices of 1. Okay. Update the distance values of adjacent vertices of 1. Adjacent vertices of 1 as well. The distance value of vertex 2 becomes 12. Vertex 2 becomes 12. Why? So let's see. So you can see from 1 to 2, the distance is 8. So 8 plus whatever the original value 4, which was assigned to 1. So the distance to 2 becomes 12. 0 to 2 becomes 12. Okay. Pick the vertex with minimum distance value and not already included in shortest path tree, not in SPT set. Okay. Vertex 7 is picked. So SPT set now becomes 0, 1, 7. 0, 1, 7. So shortest path, like we saw that from 1, like which was the shortest one. Like from 0, we compared both of those. And then the shortest path out of these two direct neighbors was for node 1, which had a path of 4. And for node 7, it had path of 8. But from 1, if let's say if the distance between 1 and 2, or the weight between 1 and 2 was like less than 3 or less than 4, then we could have considered adding that to the SPT tree before adding 7, but it is 12. Now we compared the competition or contention between 12 and 7, 12 and 8, which is the weight for or the distance for node 2 and node 7. So we came to node 7 and added this one. So we become 7 updated 7. So if we go back to the original node, so from 0 to 7 it was 8, so we will be adding that. 8 plus 7 becomes 15, and to 6, 8 plus 1 it becomes 9. So the same one, we added the distance values to these nodes as well. Pick the vertex with minimum distance value and not already included in the SPT, not in SPT set. Vertex 6 is picked, so out of the so 0, 1, 7, 6, update the distance values of the adjacent vertices of 6. 5 becomes 11. Okay. Update the distance values. Update the distance values of the adjacent vertex 6 and the distance value of the vertex 5 and 8 are updated. Got it. So both of these 5 and 8 are the values before. So in this step, you can see the value to 8 was 15, but there is a connection from 6 to 8 as well. So if we traverse this way, 8 plus 1, 9, 9 plus 6, 15. Yeah, it should be 15, but if we traverse this way, 4 plus 8, 12, 12 plus 2, 14. So when we consider it as a neighbor of 2, then it is 14 here. So so now in this step, we considered as a neighbor of 2, we added it as 14, and we concluded. We kept going that way, 0, 6, 0 step until it gets the short code as well. It should be simple to explain in the same. One we will, it's like I think I would say greedy algorithm. Like we will keep the immediate uh, immediate best path to traverse. Since it is only positive weights that we are considering, we will just go to the immediate next path. So let's see here. Okay, chart main, and it is the it is adjacency matrix. We have a graph like this, and then we have a shortest path t dot Dijkstra's of graph comma 0. So 0 is the node from which you find the direction. And then the distances are given as like from 0 to 0 as 0, 0, from 0 to 1 as 4, to 2, 12, to 3, it's 19. So those are the shortest paths calculated to each and every nodes there. So how are we calculating it? So it's called the Dijkstra's method, which is here. So what they are doing, they are initializing another similar adjacency matrix of the same length. V is the number of vertex in the node, and then SPT set is the basically SPT set will be true if vertex I is included in the shortest path tree, or shortest distance from source to I is finalized. If the shortest distance to a particular node is finalized, then we are adding it to that. Let's see. We are initializing it to the length of the total number of vertices. And yeah, like initially it will all be empty. Initialize all the distance as infinite and SPT set as false. Okay, we have initialized two of those. One is to hold the distance, and the other one is to just hold the vertex value or the included value. So this is a Boolean. If we have figured out the final path, it signifies if we have figured out the final path, shortest path for that particular vertex or not. This will hold the distance, absolute distance for that path or for that vertex. So here we are initializing for each node as distance as max value. I mean infinity, that is integer dot max value is like, instead of holding it as infinity, we are initializing it as max value. And here we are in marking it as false. So that means like the shortest path is still not determined yet. And then the distance of the source vertex from itself is always 0. Okay, from the vertex to itself is always 0. Find the shortest path for all the other vertices. Let's say in count is equal to 0, count less than v minus 1, count plus plus. Okay, u is equal to min distance of distance. Pick the minimum weight vertex from the set of vertices not yet processed to source in the first iteration. Min distance of. Okay, what is this method doing? Minimum distance. Okay, so we are what are we passing here? The distance, what is that distance array and shortest path tree set, the array of that as well. So we have passed both of that. Integer min is equal to integer dot max value and min index is equal to -1. Okay, so none of them are minimum index. For integer v is equal to 0, v less than v. If v is equal to 0 and distance of v is less than or equal to min, the distance of v this is just cosmetic changes to print it. And here, let's see, what are they doing here? Iterating through all the vertices, and then they are trying to see if that vertices or vertexes shortest path is not yet determined, and then if the distance to b is less than or equal to minimum, then min is equal to distance of v and minimum index. Okay, we are just determining the minimum distance. Okay, let's see, where was that used? U is the minimum distance. Pick the minimum distance vertex from the set of vertices not yet processed. Okay, got it. So we will have the distance initialized as much as possible for all the vertices, but we wouldn't have marked it as we have already determined the shortest path for that. So in this case, we have initialized the distance as 0 only for the source node, and for the rest of those, we have initialized it as integer dot max value. It will remain as it is. So u is pick the vertex, basically pick the minimum distance vertex. So what is it returning? So you can see minimum index. So it is just returning the vertex with the minimum distance. So in this case, the vertex with the minimum distance will be 0. So that's the source index, right? Yeah, source is 0, as you see. Source is 0. We set that process, and then you mark the source or 0 as processed is short path finalized for that particular vertex, and then we are kind of trying to add its neighbor's distance from the point of view of that current vertex, which is 0. So for v is equal to 0, v less than v plus plus, if it is set of v and graph of u comma v. Okay, we are going through all the nodes now, all the existing nodes from 0 to this one. And if that node, if node's shortest path is already not yet determined, and if there is an edge from that node to the node v, I mean, if it is not is equal to 0 means there must be an edge, and the distance of u is not equal to integer dot max value. So it's not the initialized value if the distance is not the initialized value, and if the distance of u plus distance of u plus graph of u comma v is less than distance of v. Okay, what is this one? Distance of u, which is the current distance basically, which is 0, plus graph of u comma v. So that is the edge. No, that is the weight actually, not the edge. So we have the weight maintained here, not just as 1 and 0. So the weight means the distance to that neighbor vertex. If it is less than distance of v, if it is less than the existing distance that we are maintaining in that list, then distance of v, okay, yeah, then we are just updating the distance. So if the current distance that we are calculating from this node is less, and then we are printing the solution as distance. When are we going to mark it as true? Okay, we are going to 0, and then we will go to 1 once we traverse from 0 to all the nodes. So from 0 we are checking for all the neighbors from 0, and from 1 we will be checking all the neighbors of 1 as well, starting from 0 basically. If the shortest path for that is not finalized, if it has an edge to that vertex from that current one, okay, then we are printing it. And then the time complexity is O of b square, and the auxiliary space that we use is O of b. Auxiliary space is easily understandable because we are using two. One is SPT set, shortest path tree set, and other one is distance. Both are of length as total number of words. Once we have that, that is the and. Okay, that's the auxiliary space. Time complexity is and here we have vertices, and here also we might go over all vertices, I guess. Yeah, but it is not inside. So how it is why it's not O of b cube, why it's O of b square is this could be like O of b here, O of b here, so it will be O of 2v, and around that O of b again, so O of 2v square, which is proportional to O of b square. If it was like, let's say, if the minimum distance was calculated within this loop, then it would have been O of b cube instead of O of b square. So that's the simplest way of looking at it. Calculates the path information. Okay, path information is not calculated. What do I mean is, like, let us trace back to the same path. Let's see, now for 8, but the path is 4, 0, 1, 2, 8. But that is not traceable with the current approach that we what I'm to say. Yeah, you can see there is a path from 0, 7, 8, 0, 7, 6, 8, 0, 1, 2, 8, 0, 1, 7, 8, all this way. But the shortest path is given by 0, 1, 2, 8. But we don't have any ways to trace it with the current code or implementation that we saw. It doesn't calculate the path information. Create a parent array, update the parent array when distance is updated, and use it to show the shortest path from source to different vertices. Okay, so now if we see, let's say if there is another parent array which is of length v only, and when we are updating the shortest or the minimum path here, like minimum distance. Here we are updating the minimum distance to each vertex, right? uh, while we are updating that, if we can update the parent as well. Yeah, we are updating the distance. If we update it as well, parent distance is minimal, then we can trace it back. Now if we know that, okay, to 8 the minimum distance is from 2, we will know, like from 2 also we will have a parent updated, which is 1. And then so from 8 we can go to 2, from 2 we can go to 1, from 1 we can trace it back to 0, so we can know the shortest path, not the value of the shortest. The time complexity of the implementation of this of v square, so we saw it as represented, it can be 2 of e star log v in the heap. Please look at the adjacency list representation. Next one, I'll be back. Live stream, but not many. Okay, feel free to just text me if you join here. Okay, now we looked into Dijkstra's algorithm to solve a graph represented using adjacency matrix, and we saw that, okay, it is applicable uh, only for the graphs with positive edges or positive weights, not for the negative edges. And how we could have traced the path, shortest path to the algorithm as well. So we saw all that. So now we see why Dijkstra's algorithm fails for the graphs having negative edges. The problem with the negative edge weights arises from the fact that Dijkstra's algorithm assumes that once a node is added to the set of visited nodes, its distance is finalized and will not change. However, in the presence of negative weights, this assumption can lead to incorrect results. Yeah, this is like a greedy algorithm. I would say we are just having the short sight of like what's the immediate payoff. Like if we have something as currently see that, okay, this is the best suited solution, then we are just going for that one. We are not thinking from the uh, we are not thinking from the overall point of view that in future it might get better. In the same way he's saying, like let's say to that particular graph, when I said we saw that until now to this 8 14 was this one. Let's say if we had a path to 4 as well, which was 21, And then from 4, if there was a negative weight of like 11 or something, then it would have become 13 to 8. So but we cannot foresee that, and this one would work because we have an assumption that all the weights would be positive. So if we go farther from 14 to any nodes, after that there's no way or no chance of coming back to less than 14. So that's that. However, in the presence of the negative weights, this assumption can lead to incorrect results. Consider the following graph for the example. Okay, that's good. They have given an example as well. In the above graph, A is the source node, A is the source node. Among the edges A to B and A to C, A to B is the smallest weight, and Dijkstra's assigns the shortest distance of B as 2. Okay, shortest distance to B as 2, shortest distance to E as 4, C as 4. So it will just assign the shortest distance of B as 2 and then add it to that SPT set, and like assumes that the shortest distance is already calculated for B, so it doesn't have to modify it. Okay, so PS2, but because of the existence of a negative edge from C to B, the actual shortest distance reduces to 1, which Dijkstra's failed to detect. So we have marked it as finalized 1, but from A to C it was 4, and from C to B it is -3. So 4 minus 3 becomes 1 to come to B via C. So, but yeah, we won't consider that once we have added it to that shortest path tree and finalized the shortest path. So that's why it fails for the negative edges. We use Bellman-Ford's shortest path algorithm in case we have negative edges in the graph. If there is a negative edge in the graph, then we go for Bellman-Ford's shortest path algorithm. We'll see later how it is different from Dijkstra's algorithm. For Dijkstra's algorithm, it's always recommended to use heap as the required operations extract minimum and decrease key match with the specialty of the heap or a priority queue. However, the probability is the priority queue doesn't support the decrease key. To resolve this problem, do not update a key, but insert one more copy of it. So we allow multiple instances of the same vertex in the priority queue. This approach doesn't require decreasing key operations and has below important properties. I don't know, these things doesn't make sense before we even look into the approach. So Dijkstra's algorithm using adjacency list in O of E log V. Okay, so that's the solution given, but have they explained it? No, they haven't. But they have, maybe this is the explanation and we were expected to understand from this one. Let's see. Let's see who's okay. I assume that the audio is, I'm audible as well. Let me check the mic. Okay. Yeah, everything looks right. Yeah, let's look into this one. I did not understand this point. Okay, I understand that priority queue is used and we reduce the runtime of the Dijkstra's algorithm to using the adjacency list to from O of B squared to O of E star log B, E into log B. That's what I mean. For algorithm, it is always recommended to use heap as the required operations. I mean, extract minimum and decrease key. What is this decrease key? Okay, as the required operations match with the specialty of the heap or priority queue. Okay, heap is specialized to give the minimum values of the, I mean, at every, like, we can just fill values into a heap, and then when we try to heap or a priority queue, and then when we try to extract from the priority queue, we can just get the minimum values among all the values that exist in heap, and it takes O of log n in order to adjust itself, like whenever we extract any element, and also if we insert anything new, it would take O of log n. So it will take O of log n to adjust. So that's the speciality of the heap in order to just explain it briefly. To resolve this problem, do not update a key, but insert one more copy of it. Okay, some key to resolve this problem. Do not update a key. Here we are saying decrease key. So don't decrease key. Here they are saying insert one more copy of it. So we allow multiple instances of the same vertex in priority queue. This approach doesn't require decreasing key operations and has below important properties. Whenever the distance of a vertex is reduced, we add one more instance of vertex in priority queue. Even if there are multiple instances, we only consider with distance and ignore those. Okay, so basically, yeah. So for each vertex, we are maintaining a distance as well in the priority queue. So if we need to decrease the distance to a particular node, let's say we traverse to via path and updated the distance. So how we used to manage the distance? We were using a kind of plain array at before, and we were comparing the plain array with everything like in O of n, and then we were trying to figure out the minimum distance. Now we are just updating it to a priority queue, and if that we need, in case if we found a better path from some other vertex, and if we need to update it to a lesser value, then what they are suggesting is don't remove the existing value, just add the new value or the updated lesser value. Obviously updated value is the lesser value for that particular vertex. We only consider the instance with minimum distance and ignore the other instances. The time complexity remains O of E log V, as there will be at most O of E vertices, okay, in the priority queue, and O of log E is the same as O of log V. Okay, we only consider the instance with minimum distance and ignore the other instances. Okay. The time complexity remains O of E log V, as there will be at most O of E vertices in the priority queue, and O of log E is same as O of log V. Okay, let's see. We can analyze the rather than depending on that statement. So we have added edges to those graphs. So here in this case, we have the source vertex, the destination vertex, and the actual weight or distance between those, and we have been adding it, and now we have to calculate the shortest path after that. I first might have to take a break. Let's see. Reduce it to 17 minutes. Then I've started. Okay, let's go. So yeah, so finding the shortest path here from the source is given, then comparing o dot second. What is o dot second? There is something of a type called I pair. Where is this I find? Okay. Weird in Java, like when you name a class with the lowercase, at least I haven't come across it before. Static class I pair, maybe because it's static class, I'm not sure. And it has two attributes, first and second. Got it. So what does it mean? I think it's comparing the weight instance equal to actual instance of max value, and for we have a data source and distance 0. The distance of value may be that you want to be addressing. It use PQ or hold of seconds. It's actually 0. I mean, it is like from question basically. same as the year. So we adjust it for the current vertex remaining all neighbors, and then distance plus okay, the distance current vertex. Okay, in this and vertex. So the distance to the current vertex plus the distance mean is less than the distance to the first v dot first. Okay, and the distance to the then we are whatever we calculated with the current node and pq add, and we are adding as a new I pair of distance of v dot first and distance of v dot first, distance of v dot first and v dot, node I guess, and v dot first distance to v dot first is the value. So what is v here? V is the pair, is the pair adjacency is of u, get of u, add edge. So in the edge we are adding a pair. So first is the vertex and second is the weight. Here also in the same way, vertex and the weight we are adding to each other, both of those. So notice it's written yeah, that pair, the first attribute is the vertex and second attribute is the weight. So we have added the weight here, we have compared the second's weight here and added the second's weight and the distance to u, and we are getting the current also with a new distance, the existing value from the priority queue, but we are adding the updated value. And okay, vertex distance from source for int I is equal to 0, and we are printing the same thing. Man, that was exhausting. I think we need to write this code and visually see how it is working, then I can clearly explain it much more clearly. Maybe in a debugging screen my ability to explain it will be much more better. Time complexity O of E log B, where E is the number of edges and B is the number of vertices. Auxiliary spaces O of B, which is the number of vertices. Kind of understandable. But what is stored in priority queue? In the priority queue, I'm maintaining actually the distance, I guess. And we are more concerned about the current node itself. I hope it doesn't exceed. Priority queue dot add 5 pair of. Okay, we are adding it for each vertex. So the number of vertex might increase if there are duplicates or we have added multiple times, but it will be in the order of number of vertices only. That's why we are kind of calling it as an auxiliary space of O of V. But time wise in the while loop, this will be in the order of O of vertex, and O of edges is where is it? Okay, this is the number of edges, and then in order to perform this add operation we will take log V. That's the assumption, because the size would be V, so log V. Okay, so that is there. Google Maps uses Dijkstra's algorithm to show the shortest distance between source and destination. In computer networking, Dijkstra's algorithm forms the basis for various routing protocols such as OSPF, open source, sorry, open shortest path first. And let me see. Okay, open shortest path. And then transportation and traffic management systems use the Dijkstra's algorithm to optimize traffic flow, minimize the congestion, and let's implement a graph, then a proper way to format it and print it, and then let's implement DFS, PFS, traverse DFS searches, and then let's implement it, and it will be clear. Let's do that. I think more of finishing DF and BFS and graph representation in the focus session. Implement the Dijkstra's algorithm in the focus. Okay, we need to proceed with this. For the post algorithm session, the sharp path and convention, we went both of these. We know the path algorithm now, and for adjacency matrix. At this time, the complexity for adjacency matrix representation is O of V square. In this post, O of E log V algorithm for adjacency list representation is discussed. As discussed in the previous post, that in Dijkstra's algorithm, two sets are maintained. One set contains a list of vertices already included in SPT, shortest path tree, and another set contains the vertices not yet included. With adjacency list representation, all vertices of a graph can be traversed in O of E using BFS. Okay, I establish the graph, use BFS, and use a minimum min heap to store the vertices not yet included in SPT. Or vertices for which the shortest distance is not yet finalized. Min heap is used as a priority queue to set of included operations like extract min and decrease value. Key value is O log of min heap or the detailed steps. Create a min heap of size V, where V is the number of vertices in the given graph. Okay. Every node in the node of the min heap contains the vertex number and distance value of the vertex. Initialize min heap with source vertex as root. The distance value assigned to source vertex is 0. The distance value assigned to all the other vertices is infinite. While min heap is not empty, do the following. Extract the vertex with the minimum distance value node from min heap. Let the extract the weights, like till now currently until not non-determined heap, and then we are traversing that way. For every adjacent vertex V of U, check if V is in min heap. If V is in min heap and the distance value is more than the weight of UV plus the distance value of U, then update the distance value of V. Let us understand the following example. Initially, the distance value of the source vertex is 0. Infinite for all the other values. So source vertex is extracted from min heap and distance values of vertices adjacent to 0, 1 and 7 are updated. Min heap contains all the vertices except vertex 0. The vertices is green color. The vertices in green color are the vertices for which minimum distances are finalized and are not in the heap and are not in a min heap. Since the distance for value for vertex 1 is minimum among all the nodes in min heap, it is extracted from min heap and the distance values of the vertices adjacent to 1 are updated. Okay. This is in min heap and the distance of 1 is shorter than the previous distance. Okay. Min heap contains all the vertex except 0 and 1 now. After this, these steps are done. And then again repeat the same thing. So min heap now contains all the vertices except 0, 1, 7, distance values of adjacent vertices of 7. Got it. Pick the vertex with the minimum distance from the min heap. Okay, vertex 6 is being picked. So min heap now contains all vertices except 0, 1, 7 and 6. Update the distance of the okay. The above steps are represented till the min heap doesn't become empty. Finally, we got all the shortest path tree. Okay, graph representation and adding the edges. And then finally here, distances diastras of B, graph and source. B is the number of vertex, graph and source. Priority queue over. Adjacent list node current, okay, poll that, and the adjacent list node in graph.get. Yes, less than, okay, and distance of n.get vertex. Okay, if it is greater than existing, the newly calculated distance is less than the existing distance, then update it as the minimum distance. And then add its neighbors again. The time complexity of the above code or algorithm is V of V square. As there are two nested loop while loops, if we take the closer loops, can observe the statements in the inner loop. Okay, I think we have a break time. I think we looked into this one as well. The Dijkstra's algorithms using adjacency list instead of adjacency matrix. So let's take a longer break. If the lunch is ready, otherwise I'll take a shorter break. I realized that I was talking while I was on mute. Maybe there was nothing you could hear, I guess. I just finished my dinner and came running since the break time was over. Like last 10 seconds of the break time, just I finished and ran here. Mm, so now I increase the focus time back to 25 minutes. Let's see. Now we need to implement all the graph related things that we saw since yesterday or learned since yesterday. Mainly, we'll start with the graph representations, and then we will try to implement the uh, uh, I have few things created here for queues and stacks and linked lists. I think I can go over these things some other time, but now's the time. I'll just create another package or another folder where I'll create graphs. Okay, I was just looking at it. So data structures, and so I haven't coded in Java since past 3 years. So need to get some muscle memory or some practice. I've been practicing. I've started practicing recently. I just started practicing recently. Let me know if the screen is not visible as well. I'm trying to lock the configuration in this view as well. And then let's get back to the timer and let's start it. The coding part is the, I think, one where we will be able to focus more, I guess. So let's create a, let's name it as graph.java, and then within that itself we can okay, let me close the door as well. um, okay, so graph.java, we have a graph data structure, and now how it's represented. Okay, public in next, and let's see, and then node next, that would make it as a linked list node. But what we need here, there can be multiple nodes or as neighbors, or what can we call it as, um, edges or vertices. So yeah, this looks good, I guess. This looks better. And then somehow I need to just create it as an app. Like if we maintain a list of nodes, that should be able to provide us all the values. Let's come back to it later. We have a node class or the graphs class, and then yeah, there can be so many nodes across the graphs, right? So we have a constructor here. So this is a GitHub Copilot suggesting it. Not always right. It cannot replace the developers yet, but maybe down the line, 5 to 6 years. Is it size required? Maybe not, or maybe yes. We are. why do we need to maintain a list of nodes? Let's maintain a um, map of nodes, I guess. Map of integer comma node as nodes. Yeah, that's better. And then let's initialize it as hash map. And we don't need size. And we don't need to size to initialize it as well. And yeah, got that Java util map, Java util hash map. Okay, we have initialized the graph. This would be the adjacency list representation. So for adjacency list, I have taken represented using graph for easier access. I mean, list is okay when we can reference the vertices using the index. Then it's like we are basically restricting the indexes to a certain value of type integer. Like when the indices are like or a format 0 1 2 3 4 5, then we can just make it as integer. But while coding, we should try to make it as generic as possible. In fact, not just 0 1 2 3, we should not limit it to just integer also. If we are creating a graph of, let's say, some social media friends or something, then it should be like this should be a friend object or a person object, and then this should be like a uh, this should be like friends. Or if we are defining something like a next door or neighborhood related ones, then we can define it as neighbors as the nodes. So let's go back to integer. For now, we can make it as generic towards the end once we implement everything. uh, so here, add edge and add node. So these are the things. So let me see how many nodes are created. First thing is public void add node. So add node, what the add node will do is um, basically auto-generated code. So we are creating a new node. New node would be initiated as null and null, uh, or 0 and null probably. And then we are putting that value to the hash map here. Okay, we are providing the data as the integer value. Got it. So nodes will be null, I guess. Node will be okay, and neighbors of the node would be null. And then we can add public void add edge int source destination. Okay, so here node s is okay. Nodes.get, we are getting the this looks like the code from the hack uh, from Gail McDowell that she showed in the HackerRank YouTube channel. But yeah, I don't like this source. I mean, yes, D. So let's make it as destination. I don't think we have to mention it as node. It's kind of implicit. Let's modify it as okay. We can use this as, I think I remember, if I remember correct. I remember from idea there was a refactor. Okay, rename symbol. Okay, VS Code also supports it. That's good. And rename symbol destination, and here, yeah, source and destination. Okay, let's mark it as rename it and source, make it a source node. I didn't see that the parameter name is same. Okay, now it's correct. Source, yeah, that should be right. And then another thing is I was looking into something. So we get the source node and the destination node from the map. We have the pointers or the map representing from integer to that particular node object. So it's giving the node object. if source node dot neighbors is equal to node null, source node dot neighbors is equal to new node. Okay, this neighbors, let's make it as an array list uh, instead of static list. Array list of neighbors. Array list called neighbors. Okay, detected. Is there a delay or it's okay? We got it now. And then new node post dot neighbors. Here we can define the constructor also. When we define a node, it should instantiate the neighbors with an empty array list. So we don't have to do this, I guess. We don't have to check if the source dot neighbors is equal to null. It won't be null. Source dot neighbors is equal to okay. What happened here? Okay, this is all auto generated. I'll just remove this. Source dot neighbors won't be null. So it's time to add. We can just do this thing. Source node dot neighbors dot add destination node. Destination node dot neighbors dot add is source node. And what they are trying to do here. Okay, that should be good enough just to create an edge between two nodes. So the edge is created. So basically we are connecting two nodes here. So in an undirected graph, I'm adding the neighbor, source node's neighbor as destination node and destination neighbor as source node. That should do the trick, I guess. That should be good enough. And yeah, we have the mapping for those things. Yeah, everything's sorted there, I guess. Yeah, nothing else is required. If we need something while defining DFS and BFS, we can come back. Wow, this is cool. Print graph. It is printing the graph here. It cannot be 2D graph. That's a loss. I'm just thinking if there is a way I can make it 2D and connect them. I think it's too much work if we need to do that. We might have to use certain libraries and things like that. We can't do it as it is. Okay, so let's test it out first. Maybe, yeah, this is cool. G.add node 1, 2, 3, 4. 4 nodes are added, and from 1 to 2, if there is an edge, 1 to 3 there is an edge, 2 to 3 there is an edge, 3 to 4 there is an edge. And print graph. Let's run this one and see what's the output. Wow, it takes a lot of time. Still compiling, resolving dependencies, and now it ran. Okay, So let me make it a little bigger for you to. Or what I can do is, how much of the space I'm using here. Can move the terminal too. Okay. How is it? Better. We don't need a lot of space for this. And we don't need a lot of space for terminal as well, as long as we are not executing it. So we were able to print the graph. Let's make DFS and BFS. I mean, for my practice, I think I should just disable Copilot for now. Editor inline, explain, fix, generate, add files to chat, add inline chat. Yeah, Copilot. Okay. So now it says that it is disabled. Let's see. So now we just added the edge, and now it's time to, let's say, do DFS traversal public void, and I will try to print it rather than search DFS traversal. So we can make it as in source. We can take a source as one of the input and then see if I can traverse. v.dfs source we can provide as 1. Okay, so I think it was a good thing yesterday what Gail McDowell was doing in HackerRank. She was trying to get the so yeah, calling this as nodes would be kind of not so good. I guess we can call this itself as a graph, basically. That itself, that represents the graph very well, actually. What I can do, let's see. I think I can keep the graph classes separate. I think I can keep the operations class as separate one, and graph can be just this adjacency list with it can be just this adjacency list with, I'm just trying to be creative or over smart, I guess, with how I am representing the graph traversal or just representing the graph in my code. Let's try to get the basic version up and running, and then I can go into get into all that details. Whenever I look into the code, I get excited here. So DFS traversals, let's see, DFS traversals and nodes.get source. So now I should create another method called DFS traversals, not traversals, it should be DFS traversal. And then here it will be node source node, and then here. Okay. For the type graph. Okay. Yeah. Now what I'm checking. I need to traverse from. Okay. I might need a visited set of probably integer. So they put a new hash search, and then I can send that as well as part. Copy, copy, don't delete. Yeah. So this is the visited one. And then what else I need? Java tutorial, public.java tutorial. And then here the method get object in the type graph is not applicable for the argument int set of integer. Okay. Yeah, visited should be outside here. So yeah, now it should look right. So if what should I do here? If visited dot contains our source node dot what is it, data. Yeah, if it contains, then just return, do nothing else. First thing is visited dot add visited dot add source node. Okay, and then once I add the current node, what should I do? It should, I'll not mark it as source node, I'll mark it as current node since it is the DFS traversal. Yeah, so I marked it as current node. Okay, visited dot add current node. Once I do that, what should I do? Next thing is it is in the visited. Now I should iterate through each of those and then go deeper into that. Like I should iterate through each of its neighbors basically. So let's go back to this one. Node neighbor. So here neighbors of the current node. Yeah. Now I have the neighbors of the current node. And then what should I do? I should call DFS in each of them. Then it will go deep in each of those things. DFS traversal in each of those nodes. So, and then it will be, I'll have to pass the visited as it is. And I have already marked the current node as visited. Or what I can do is I could have marked it before sending also, rather than here. I could have just marked it as visited and also mark the source as visited here. So what is the problem with this one? Okay, current node dot data. I think I can just add the node only. Why did I end up adding here? Because I hate trusting just the values. It could be anything. Yeah, this looks cool to me. So in the DFS traversal, let's write this graph representation, and then we can think of what should be the solution for DFS. Let's calculate it in theory first. Let's switch to our other LeetCode stream. And where's that? Yeah. Okay, this is the graph that we defined. So, wow. Okay, we don't even need this. 1, 2, 3, 4. These are the 4 nodes. I should have made it more interesting. I chose a boring name 1, 2, 3, 4 as the other tutorials only. I like having some real world things like friends or something. I should have gotten a feel of that. We could have gotten a feel of the real world application or the places, name of the places or anything. Yeah, now we have this. So there is a G, we created a graph and we added 1, 2, 3, 4, 4 nodes. So this is done until this one is done. So now we need to add an edge between 1 and 2. So in order to add an edge between 1 and 2, let's do this. And it is, since it is undirected graph, I'm not having any arrows here. 1 and 2 there is an edge, and there is an edge between 2 and 3. There is an edge between 2 and 3. Okay, 2 don't come. Am I sharing correctly? My phone, it looks weird. Okay, maybe it's the old version. Okay, rotate please. Got it. 2 and 3 there is an edge, and then there is the edge between 3 and 4. Okay, let's copy this edge. Okay, I need more time to implement this after. Let's not take a break for now. Let me take a break after this implementation. So I'll pause the timer for now. Okay, 3 and 4 there is an edge. Okay, 1 and 2 there is an edge. 1 and 3 there is an edge. 2 and 3 there is an edge. Okay, we skipped 1 and 3. Okay, let's add this one as well. An edge between 1 and 3. Okay, this is how the graph is looking like. So now our source node is 1 here. So if we start from 1, then we can go to 2, and then 2's neighbor is 3, 3's neighbor is 4. So it has to traverse this way. Let's take a little complicated example. Let's add another node here. 5. And then let's make it as okay. And then there must be another node to 5. So now my ask is, okay, let's remove this one also, the node between 2 and 3. Then I can see the difference clearly, how to strike it off. Okay, 2 and 3, you are removed. You are added. Nice. And then I need to add a node between 1 and 5. So now I would know the clear difference between DFS and BFS traversals. So for DFS traversal, I should expect an output of something like 1, and I removed this one, right? 2 and 3, yeah. So I have a edge from 1 to 2, got it. And I have an edge from 1 to 3, yeah. And then 3 to 4, yes. And then I should have an edge from 1 to 5, yes. Now before coming to 5, either it should be like 1, 5, 3, 4, 2, or it should be 1, 2, 3, 4, 5. So 4 should follow 3 basically. Neither of these things should follow 3 in DFS. And in BFS, breadth first search, uh, 2, 3, 5 should come before 4. We should traverse the immediate neighbors before going to the farther neighbor. That's the concept, right? We understood it yesterday. So here the closer neighbors are 2, 3, 5. Before we should traverse this one in BFS traversal. In DFS, it doesn't matter. Once we go to 3, the next node that we traverse shouldn't be 2, shouldn't be 5. It should be 4. But I don't know the ordering between or the priority between 2, 5, and 3. One of these will be picked. But when the 3 is picked, next one should be 4. It should not be 2, it should not be 5. Got it? We got it. So the expectation is 4 should be printed immediately after 3. So in case of BFS traversal, here in case of BFS traversal, what is it? 2, 3, 5 should be printed before 4, which is in the next level. That's the just let's make this change in our graph also. Let's go back to the graph. Okay, we added another node in this graph. So the node is 5. Okay, and then we removed 2 to 3. So let's comment it out. And then we added a edge. G dot add edge between 1 and 5. So that's it, I guess. And then now from 1 we are traversing. Okay, and we have the DFS traversal kind of, but we haven't written the print statements. So if we just return without printing, we don't have to print here. But if we are coming till here, that means we are traversing that node. So we can just print I think it's cool to make it as visit, like whenever we visit a node, it can print that way. So we could have abstract it away into a separate method, but that's the way it should be. I mean, we are not even sure like visiting it just means just one line of statements in real world scenarios. So can be anything. So visiting means we know, okay, we have to print the value of that node. So what's the node value? Current node. Data. Yeah, that should be good. So now let's print it again. I'll clear this one so that it can print it in the upper half only. Running and compiling, it is a bit slow. I don't know why. Maybe because a lot of tabs are open. And oh my gosh, I forgot to go back to the ID here. I just made the modifications to add this, add the node 5 here, and then added an edge between 1 and 5. That's it. And then I just added a print statement here, just before marking it as visited. We should not print it here because it can happen multiple times. It can come to multiple times to the same node, but it will return as it is without adding the neighbors. Okay, so now we see here 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is the order in which it is printed. Let's go back to the that graph and compare it. I think I should have held the graph in some part in this screen itself. That would have been cooler. Let's go back. LeetCode stream. Yeah. So the order in which it is printed is this is GFS 1, 2, 3, 4, 5. What did we say the rules should be? 4 should be printed immediately after 3. 4 is printed immediately after 3. So I made it as print ln. I could have just managed with print only. I added those dashes as well. Print instead of print line, it should print in the same line. So yeah, let's go back. So 1, 2, 3, 4, 5. 4 should be printed immediately after 3. 4 is printed immediately after 3. Let's make some changes in the code for some other test cases and see if that also works. So here, let's add a edge between 2 to 4 instead of 3 to 4. So now 4 should be printed immediately after 2 and then not immediately after 3. Basically 1 to 3 we have a destination, so the graph would look like something like now let's go back here. Now I made the graph look like, okay, 1 to 3, it is like this. There is a edge between 1 to 3, but there's no edge from 3 to 4, but there is an edge from 2 to 4. Now 4 should follow immediately after 1. So 4 should follow immediately after 2, I mean. So let's go back and run. 4 should be printed immediately after 2. Okay, let's check it. Main, come on. Where's the run hint? Oh man, there's the main method. Okay. So this is the print statement. I made it, I just removed the print ln and just made it as print. So now you can see 1, 2, 4, 3, 5, and our expectation was 4 should be printed immediately after 2. So the DFS is working as we expected. It will just keep going to the neighbors. We can make it a little more complicated also and try it, and it should work, and I am quite positive that it will work. So I think DFS is working. Maybe we can add another node like this. Yeah. Okay. So here I can add a 6 and I can add a 7. So let's add a 6 and a 7. And then let's add an edge from 4 to 7. to escape this. Drawing tools are like so hard to handle. Okay, 3 is here. So from 3 to 6, let's say. So now the rules is 6 should be printed immediately after 3 and 4 and 7 should be followed after 2. I mean, it should be in the order 2, 4, 7 and 3, 6. That should be fixed. I'm not sure if it will be 1, 2, 4, 7 or 1, 1, 3, 6. I don't know which one will come, or 1, 5 and then these will comes. But as soon as 2 comes, 4 and 7 should be printed. As soon as 3 is printed, next should be 6. So that's the rule. Let's go back. So now we have created 2 more nodes, 6 and 7, and we have added an edge from 4 to 7 and 3 to 6. So I didn't add that here, but I'll just add it in the code directly. Okay, so in the code, I need to add 2 more nodes. So one is 6 and the one is 7. Okay, and then we need to add 2 more edges. Okay, so the edges were from 4 and I told I need to add to 7, and from 3 I'll be adding to 6. So it should be 2, 4, 7. 2, 4, 7 is fixed order, 3, 6 is fixed order. That's the way it should be printed. Let's go. Does it have to be explicitly saved? Wow. Oh. Virtual machines, and there's the compiled code. First I need to compile. So this is not compiling, this is just running the code. Not run test on Java. Okay, 1, 2, 4, 7, 3, 6, 5. So the rules was 2, 4, 7 that is fixed and 3, 6 that is fixed. So that's how it's working. After 1, 2, 4, 7, 3, 6, 7, 5. So let's go back to the whiteboard and check. Last time I'm not gonna verify it anymore, and then we can move on to BFS. Okay, we can see this one. So as we had said, 2, 4, 7. After 1, it went to 2, 4, 7, 2, 4, 7. And then it went to 3, 3, 6. 1, 2, 4, 7, and then came back. No neighbor came back. No neighbor, no more neighbor came back. And then it went to 3, the next neighbor. And then from 3, there is another neighbor 6. It just traversed the entire path of 6. There's no neighbors. And then 3, it checked if there are any other neighbors other than 6. No. So it went recalled back to 1. And then it was done with 2, and the only neighbor remaining is 5. So traversed 5. That's it. It's printed. So now this is done. So let's go back to what? Let's go back to BFS implementation. It should be quite similar, but we cannot code it as easy as possible. This is easy to look, but we cannot miss a step. The orders and everything, mapping it to mind is a little difficult, I feel, like until we have the muscle for that recursion, because it's like yeah, we have to mark it as like we have to move back if the visited is not marked as, or if it is already in the visited, we don't have to do anything, no ops. And then first statement, when we come, we are marking it as visited, and then we are iterating through each neighbors, and then we are running the traverser for each of those neighbors. So it keeps going deeper and deeper before we exit from this one. In BFS, what we do is we will just iterate through each neighbor, and we will just add it to the queue, saying that okay, you will come next, but we already have a queue, and there are people more senior than you who are waiting to traverse. After that, your chance will come. That's the simplest way of explaining, I guess, according to my knowledge. I think I did good. That was intuitive. So yeah, that's exactly what it does. It oh, sorry, why am I copying it? It will be, let's implement BFS traversal. Okay, what do we need here? In source node, in source. Okay, so we need a source node here. Before we do anything, let's get the node start. Get source. We got the source node, and then we have to define a queue mostly, most like more than often. Every time we need a queue of type node. Let's see, new linked list, and then we usually iterate through the queue until the queue is not empty. We are iterating through that queue. And here also, what do we do? So we are initializing the queue by just providing the source node. So that's the current node we have. So here, let's see, is equal to node. Okay, let's get the first node, whatever the next pending one is there. Why this is on auto import, work fast. Okay, current node queue.poll, that's there. And then what we'll do, queue is not empty. So if the current node is there, then I have to mark it as visited, one thing, otherwise we will keep running around it like in cycles. Mark, let's manage integer for now. We are assuming there is no duplication of values, so that's why integer works here. If we thought there could be duplication of values, then I think then it was better. Like if the name could be different, name could be same, name of friends can be same. So in that case, like rather than maintaining value, I think we could have maintained. Let's maintain node. What are we losing here? A new hash set. Got it. So yeah, so now it doesn't matter. We can have duplicates in the graph also, so it would handle based on the identity of that particular node instance. So okay, current node is equal to queue.poll. Okay, we got the current node, and then visited dot okay. Okay, let's do one thing. Let's not add it the queue itself if it's already visited. Otherwise, we will check the we'll just add it to visited here. We are checking the visited in the neighbors, not here. We are adding it as visited. Now, let's iterate through all of its neighbors. Okay, we know here now. If visited dot contains neighbor, then what should we do? If it does not contain neighbor, then let's do this. Okay, then add it to the queue. Basically, tell that node that okay, your turn will come. Just wait for it. Queue dot add neighbor. Yeah, you're saying now in this case, for example, in the previous case where okay, let's run this one. Gosh, let's see. And now we are still printing the DFS. We haven't called the BFS. So just to imagine the graph for you, reimagine the graph for you, what I'm doing here. I still haven't called the BFS traversal. So yeah, you can see this. 1 has neighbors 2, 3, 5, 2 has neighbors 1, 4, 3 has neighbors 1, 6, 4 has neighbors 2, 7. Wow, yeah. 5 has neighbors 1, 6 has neighbors 3, 7 has neighbors 4. 1, 2, 4, 7, 3, 6, 5. So that's the order. So now what should we do? So now 1 has neighbors 2, 3, 5. So that means 2, 3, 5 should be printed immediately after 1. It should not go to 4, it should not go to 7, it should not go to 6, because 2, 3, 5 are the closest neighbors to 1. So the seniority is respected here. So once you go to the queue first, you will be getting the priority. So you are in the queue. So you have to maintain that order as the name suggests. There's no logic, not much logic here. It's like common sense. You are in the queue, 2, 3, 5. Your turn will come. You are added. So 1, 2, 3, 5, and then it should be like, okay, 2's child, which is 7, should come, and then 3's child, which is 6, should come. 5's child, nothing. So 5, and whatever the 7th child should come. Yeah, 6th child, and yeah, it goes on. Let's see. Let's go back to that screen, that whiteboard. Was I sharing the screen all this while? Man, I need to do a much better job at this. I was explaining here. Yeah. So I think for this explanation it's fine, but I was writing the code. I wrote the code so elegantly, so fast. Source node, I got the source node, and then queue, I added it, and then queue.offer, like I just created a new queue. I got the source node, and then I added the source node to the queue, and then I created a visited hash set, and then while the set is queue is not empty, I'm just traversing through it, and then I'm polling for the current node and adding it as visited, the current node, and then I'm going through each of its neighbors. If it is not visited, then I'm adding it to the queue. If it is visited, then I'll skip it basically. So what's the difference in logic there between DFS and BFS? In DFS, I was going through each neighbor node and I was kind of trying to execute the DFS for its neighbor immediately when I encounter it. I was not waiting for its next neighbor here. But in this case, I'm not executing or going through the code or logic immediately. I'm just adding it to the queue. Okay, your turn will come. Just hold on. There are more seniors to you who are already added, so you will be added on top of them. So that's what we are telling. But in the stack or in the in that recursion which uses stack internally, so it was just going appending it to the call stack. Okay, this is my first neighbor. While adding the first neighbor itself, uh, I was telling, okay, go and execute the DFS for this neighbor, and then that neighbor will save the state of that call stack and then goes to its neighbor, and then it takes its first neighbor and prints it, and then goes to its neighbor. And then once all the neighbors are covered in the leaf, and it will recoil, and then okay, we'll check, okay, are there any more neighbors left? Then okay, it will execute for that neighbor and then recoil, and it eventually comes and execute each of those. So in this case, that's not true. In this case, the senior nodes who are added into the queue, they'll get the priority, and you guys have to hold on when you are in the later nodes. So let's execute it and check if that's true. G dot BFS traversal and 1. Okay, in this case, what is expected? 1, 2, 3, 5. After 1, 2, 3, 5 in any order should follow. 2, 3, 5 should follow, and then the other ones, and then 4 and 6 should follow. 7 should come late as per this graph, because 7 is like at the farthest distance from 1. That's why. Yeah, it's not like I hate 7 and it will come last. It's at the farthest distance. Okay. Okay, did I print? No, I did not print. Wait, man. That was BFS. Sorry, that was DFS. So here where I'll print. I'll print after the, just before visitor, marking it as visited. I'll print it as the same thing here. Let me get this same print statement. Yeah, that should work. And okay, BFS and BFS traversal. BFS traversal, and then let's print it in another line. Let's print it in another line. And let's come to the left side and run it. Okay, wait for it. Wait for it. Okay, this is the DFS traversal. Go. Yeah. So DFS traversal is like this. Yeah, correct. So in DFS traversal, 1, 2, 4, 7, 3. What did I say in BFS? It is 1, 2, 3, 5. 2, 3, 5, which are immediate neighbors printed first, and then 4 and 6, and then 7 is printed last. I think it's self-explanatory now in this case. We can go back to that graph and see. Like I'll just mark whatever I have printed here. Okay. So here you can see, and this is BFS traversal. Here after 1, 2, 3, 5 are the immediate next level or the immediate neighbor. So those gets the priority. 2, 3, 5 are printed. And the next level is this thing, 4 and 6. 4 and 6 are printed. 7 is third level or farthest distance from this one. So 7 is printed last. Oh, man, I'm done. So another thing is I needed to cover the matrix representation, I guess, adjacency matrix, but I can do it later. Next, let's tackle the weighted graph and implement the Dijkstra's. After that, we can move on to the next algorithm. And then let's move on to some problems based on this graph. Okay. I think this was product. I love coding, man. This is what gets you high. Coding made me feel alive out of all this live streaming thing. Everything else was kind of taking out my energy. Are there any viewers now? Man, I've been working so hard. Nobody's watching. Yeah, you should be working when nobody's watching. Let's see. I'm just taking some break now, just to get the steam off. Are there any viewers? I don't know. Tell me if you are there. No? Tiring, man. Live streaming is not easy. I don't think I've spoken so much in like a week as much as I spoke in this 1 hour. Last 1 hour. Yeah. Takes a lot of energy. Okay, let's take a break. Short break, 5 minutes. Let's get back to Dijkstra's algorithm. Got it. Go back. Wallpaper. Okay, let's get back to the business now. Hope you guys can hear me. Hear me all right? So yeah, sorry. Let me move. Okay, let's do this one now. So what we thought, we'll focus and implement the weighted graphs and Dijkstra's as well. Let's do that. Let's start the focus timer. Let's get to the IDE. First thing is we have the graph, but we do not have a way to maintain the weights in that, right? So how can we, let's just think for a bit. How can we maintain the or manage the weight? So now the connection holds the weight or the edges holds the weight. So in this case, when adding an edge, between two nodes or two vertices, we need to add a weight as well. So how to do that? When we added the edge, so basically what it means was it just said what are its neighbors. So now we can create another node with weight. Okay, so or let's create another graph altogether. Let's see if we can merge it later. So what am I doing here? With weight. then how to name the graph should be graph, yeah. And how to name this graph, that too should be an actual graph. I don't know, I didn't focus so much, I guess, while naming it. Wants to make refactoring changes with this file. Okay, yeah, it made this one also as graph. So in the main method here, graph, yeah, everything looks all right here. File name is graph as well. I haven't added the test cases. Like I have added the main method and tested it here only, but I didn't add the unit tests in like this, something like I kind of write some unit tests using JUnit and those. So this is very clear as well. But yeah, we can look into those methods or practices later. Let's try to make the efficient use of time as of now. So now we need to define graph with weights. So public class okay, node with weight. I think we could have managed the other graph class also in this one by just having weight as 1 by default, 1 for everything. And while considering DFS and BFS, we didn't have to consider that weight. And while writing Dijkstra's, we could have considered that weight. So let's see, we can combine it or not. Okay, as of now, I'll just mark as public int data, public array list of integer array list, sorry, with weight, those are neighbors. Public wait, so this one, I think Copilot developed the boilerplate code for us then, so we didn't have to do it. Okay, so node with weight class is defined, and now let's see, let's create a main method for these test cases. I like Copilot a lot. So here, let's see, we need to define a graph with weight. Okay, and then graph dot add node. Okay, let's say I added 5 nodes. Okay, in order to add nodes, let's see, public void add node in data. This chart. Okay, we wanted to maintain a list of or a map of nodes, right? So public map of map between integer and node. Okay, and where do we initialize it? We are initializing it in the constructor for this method here. This chart node is equal to what is it? New hash map. Initialize it as a hash map. Why is it complaining? Because map is not defined. Okay, now it should be satisfied. Okay, add nodes. When we try to add nodes, it should create a node. So basically, nodes dot put value is data, comma, new node with weight of data. So yeah, and then let's add an edge here. Edge from um, 1 to 2 with the weight 4. Okay. Let's add it like 0, 1, 2, 3, 4, like what we studied in that example, so that we can take the same example which was in the GeeksforGeeks website. So this would be 0 to 1, and then I think it was 0 to 7, and with the weight of 8, I guess, if I'm not wrong. There are 8 nodes defined. Okay, 9 nodes, including that one. 0 to 7. Let's see. Let's go back to implementing this method. So in order to add the edge here, so whenever we added the edge in the new array list, if we added an edge, okay, that cannot maintain it. Like array list has only node with weight. So what we can do is we can create a pair type with name pair of node dot and integer. Integer is the value of that weight. Or we can create a custom type here. Nah, it will be too much nested. Public. So in the edge we can define node with weight node, and then int weight. Okay. And this can be an array list of edge. Okay, this makes sense here. I think, yeah. Created a list of edges from the node. Yeah, sounds also good. And add an edge. When I'm adding an edge, what should I do? And this is initialized by data, and okay, this is edge can be initialized by this one. Okay. And I'm adding a graph. Okay. Okay, got it. So if I do this one, so here node with weight node 1 is equal to nodes.get. Okay, int from to int weight. Okay. Okay, just mark it as from node, mark it as to node, and then what we can do is from node dot add in from node. What are methods that we defined? In node with weight, there's nothing defined. Okay, we have our neighbors defined, and neighbors is of type public only, so we can add to neighbors. Neighbors start add new edge to node comma. Okay, so now in the edge class, let's define public edge node in weight. Okay, and then what can we do? Perfect. This should look good. Type mismatch, convert from int to graph with weight. Yeah, this should be node with weight. Yeah, you are right. So now here node with weight to node, got it, weight, perfect. And then now to node dot neighbors dot add new edge from node and weight, perfect. Okay, now everything is added. Okay, I think we have added, we have okay, perfect. Let's print the graph now. print it in a good way so that if someone views it later, they should be able to understand what's getting printed. Okay, we know that all the nodes are there in the map, so let's traverse through that map. The map, what's there? Integer, comma node with weight. This is like an entry, I guess, and yeah, nodes. We are iterating through that. Node start. Node start entry set, and this should be this format. Okay. Do we need the entry set or do we just need the key set? I think we can just manage with the key set. If we just manage with the key set, int node. Okay, so now let's print this one. Yeah, I think everything doesn't support. Okay, the node name, and we will have the values printed. So in order to let's define it here, how to print it. Node with weight. How can we print a node with weight? Let's see if we can do this. I think we can use string.format so that we don't have to run into these issues. Okay, nice. So now we know how the list is printed. So do we know how the edge is printed? No. So public. Okay. Comma in between. Okay. Let's see. Let's run it again. Okay, now it's much better. Is it visible here? It is not. So let's clear it and rerun it. It's good to code with the comfortable programming language. You can play around a lot, so much confidence. So you can see here. So it is like from node 0, there is an edge to node 1 with the weight 4. And the same from 0 to 1, if there is an edge with weight 4, that means from 1 to 0, there is a node with edge 4. From 0 to 7, there is an edge with node 8. So in the same way, from 7 to 0, there is an edge with node 8. So that's what it means. Got it. So let's see how we can recreate the other one. Let's go back to the focus mode without taking break again. Yeah. Let's go back to the example that we saw for Dijkstra's algorithm. So here, yeah, this was the example that we were seeing. I don't know if there is a way to memorize it or copy it. Mm. You can write the code here somewhere. Okay, I'll write from 0 to 1, there's an edge with 4. From 0 to 7, there's an edge with 8. Now from 1 to 7, okay, we might even have the code actually to define these edges. Okay, graph.get 0. Let's take this and go back to the IDE, define these edges. Away, down as well. So 0 to 1, 0 to 1, 4. That's 1 to 8. Make it up. 1 to 2, 8. 0 to okay, 0 to 7, 8. First thing is I had the same thing, so I didn't notice that first. 0 to 6, 3, and 1 to is 8 or 7. And 7 is 8. 1 to 7 is 11. Let's copy this one. Okay, this one is done. So now 7 to 11. 1 to is 7, 11. 7 is 11. 1 to is 7. 1 to 0 is 2 is 8. 2 to 1 8. Okay, I have to continue from, and 2 to 1 is 8. So these things are gone. Enter. 3 to 7 is, sorry, 2 to 3 is 7. 2 which 4 8 7. 2 to 8 is 2. 8. 2 to 5 is 4. 2 have not just. Let's copy these. These are all merged. Okay. Now 2 to 3 to 2 is 7. 3 to 2 is 7. 3 to 4 is 9. 3 to 4 is 9. 5 is 14. 5 is 14. Okay, got it. Three done. Now one more. Get up the syntax. 15. 3, 9. Then 4 to 5 is done. 5 is done. 5 to 6 is 2. Oh, that's redundant values, I guess. Adding it to the adjacent list. So 1 to 0 back. With a different weight and wait, what did I miss? Let's go back and check. Man.